Okay, so let's just take a look at how we created the probability distribution after taking a look at all of the possibilities that can happen and all of the various probabilities. All right, so just remember we defined the random variable x to be the number of student representatives who oppose the funding of the interest groups. So now when we create the probability distribution table, we know that x is defined. We know that it's the number of student representatives who oppose the funding of interest groups, and probability of x is the probability of that occurring. So when we say 0 here, that's saying that none of them oppose the funding of interest groups, they all support it. So up here we're going to take a look at this probability, that's the 0.216. Okay, this is when one of the students oppose the funding of interest groups. So up here we want to go and we want to find all the places where only one opposes. So we have one opposes here, one opposes here, and one opposes here. So we're going to add those three probabilities together to get the 0.432. And then the fact that we have two that oppose, let's look at all the possibilities of 2, 2, 2. Okay, we're going to add those three probabilities together to get 0.288, and then the probability that all three oppose is the 0.064. There's only one possible outcome in that case. So it might be difficult to come up with this probabilities without having the list of all the possibilities that could occur and looking at those individual probabilities to come up with your combined probabilities for your table. All right, so let's take a look at letter D. So it says express the event. A majority of the advisory board opposes funding in terms of X and find its probability. So please keep in mind that a majority means more than half. So if it's 50%, that's going to be, greater than or equal to 50%. So you have to understand what a majority means. In this case, a majority is going to be more than 2. So when we say the probability that X is greater than or equal to 2, we know that X was defined as the number of student representatives who oppose the funding. Okay, so more than 2 oppose the funding. We have 2 or more oppose the funding. So we have the probability of 2 plus the probability of 3. Add those together to get 0.352. So just remember that majority means more than half. Keep this in mind as you're answering questions in your homework assignments and in your tests and quizzes. Okay, so let's just take a look at some long-run probability. So for the probability distribution of funding question, remember that X was the number of student representatives who oppose the funding of interest groups. Here's our table that we talked about on the previous question. So what happens in the long run? What happens if we take many samples of 3 students and check to see the average number of students who oppose the funding of interest groups? So this isn't the average number of students, this is just the probability that 0 oppose it, 1 oppose it, 2 oppose it, or 3 oppose it. But if we did this over and over and over again, what is the average number of students that actually oppose the funding? So on average, in the long run, how many students do we expect to oppose the funding of our interest groups? All right, we're going to talk about that on the next couple of slides, and that's going to be something called the expected value, because how many people do we expect using these probabilities, okay, on average to oppose the funding of interest groups or other questions that we might answer. So before we go back to that one, let's just take a look at some Vegas games and roulette. So one wager players can make in roulette is called a corner bet. So to make this bet, a player places his chips on the intersection of its 4 numbered squares on a roulette table. If one of these numbers comes up on the wheel, the player bet $1. The player gets his dollar back plus 8 more. Otherwise, the casino keeps the original $1 bet. All right, so you want to understand what these mean. So basically, in one case, the player bets $1, gets his dollar back plus 8 more. Otherwise, the casino keeps the dollar. That means that essentially you're paying $1 to play the game. You don't have any net gain. So if X is the net gain from a single $1 bet, and when we're doing these questions and taking a look at these probability distribution tables, you want to be really careful about what X is representing. It's the net gain from a single dollar bet. So when we make the table, the value is going to be how much you win from a dollar bet, not necessarily how much you have spent. Okay, so just be careful with that. We're just looking at how much we win. So the possible outcomes of X are -1 or 8. Well, because X is the net gain, we're either going to lose $1 $1 or we're going to gain 8. So notice there's not a 9 here. It's not a 9 even though you got your dollar back plus 8 more because X is the net gain from a single $1 bet. All right, so X is equal to 8. We're only getting $8. So what's the probability of those occurring? So losing a dollar is 34 out of 38. There's only 4 places on that table where you're going to actually get $8 back. Okay. So once again, notice this is $8 and not 9. We're looking at the net gain. So let's just say a player were to make this $1 bet over and over and over and over again. So they're at the casino and did this 1,000 times. What would your average gain be? This question is basically asking you to find the expected value or the mean of this discrete random variable. It's basically like taking an average. However, in this case, we can't just take an average because not all outcomes are equally likely. So -1, losing a dollar, has a 34 out of 38 chance, and gaining $8 has a 4 out of 38 chance. So if we were to do this over and over and over and over again, what would be the average amount of money that we would win? Well, I can't just take -1 plus 8, 7, divide that by 2 and get 3.5 because that's assuming that each of those have an equally likely a chance of occurring. In this case, they don't. They have different probabilities of occurring. So when we take a look at discrete random variables, we follow the same strategy we used with any quantitative data. We describe the shape, the center, the spread, and identify any outliers. The mean of any discrete random variable is the average of the possible outcomes, which is what we're just asking on the last 2 slides. What's the mean or the average after rolling the roulette rule over and over and over again, okay, after choosing students over and over and over again. And that mean comes from the outcome weighted by the probability of each of the individual events occurring. Okay, so let's suppose X is a discrete random variable with the probability distribution. So here's our value, here's the probability of each occurring. To find the mean or the expected value, what we're going to do is we're going to multiply each value by its probability, then add all the products. So the mean of a discrete random variable is the expected value. Basically, it's like on average, if you do this over and over and over again, how much money can you expect to win? So all we're doing is we're taking the value times the probability, value times the probability, value times the probability, and then adding all of those together. So that's what this sigma notation means. It means take the value times the probability for each of these, add them up to get the expected probability. So like I said, the reason for that is on the previous page, if we lost a dollar and won $8, if we normally find an average, 2 possibilities, add the 2 together, divide by 2, but that's assuming that they each have like a 50-50% chance of occurring, that each of those are equally likely. Well, in this case, we're saying this one has a 34 out of 38 probability of occurring. The second one has a 4 out of 38 probability of occurring. So if I average those together, given their probabilities, what is the amount of money I could possibly win? Okay, so let's take a look at our roulette example again. So if a player were to make a dollar bet over and over and over, what would be the average gain? Well, the average gain would be we're losing a dollar times 34 out of 38, because 34 out of 38 times I'm going to lose a dollar. And then $8 times 4 over 38, because 4 over 38 times I'm going to win $8. That gives me -3 over 38. Okay, I'm multiplying these together. Okay, and then adding the 2 to get -3 over 38, or basically losing 5 cents if I do this over and over and over and over again a million times. Like I said, it's not 350 because I'm not going to add these 2 together and divide by 2, because most of the time I'm going to lose money and sometimes I'm going to win. Okay. So if you're asked to interpret what that means, it's always the long run expected value or the long run average. It's not just playing this 2 times, it's playing it over and over and over and over and over again. So if you were to bet a dollar over and over and over again, the player's average gain would be about 5 cents. All right, so what if you're asked a question about expected value or the mean of a discrete random variable, what would you see on the formula sheet? Number 1, you will see this expected value on the formula sheet, so just understand that this is the summation of your random variable times its probability for each individual value in that table. If you're asked to interpret the expected value, what does that mean? That means after many, many trials, that's the expected value, that's the average. So in the long run, the expected value will be, that's what you want to state, in the long run, after playing roulette many, many times, I would expect to win blank. Just make sure you put it in context of the problem. And this is tricky because it's hard. This is kind of hard to sometimes make sense of, especially when you get into questions that involve like people or how many people oppose the funding. Don't ever round the answer with expected value. You might be like, this is crazy. Absolutely. But if you're expected to win $1 and 0.267 cents, don't round to 1.27 or even $1, because that is not the same. That changes the probabilities, because remember, this expected value comes from the probabilities, and if you are rounding it, you're essentially changing the probabilities that you got to get your answer. Okay, most of the time the expected value is not going to be one of the probabilities on the table. It's going to be an average of all of those probabilities. Okay, so let's just take a look at roulette again. So on a red-black bet, players either lose the dollar they bet or gain $1. There are 18 red, 18 black, and 2 green slots. Show that the red, black, and corner bets in roulettes have the same expected value. Interpret the expected value. So this one's different. This one is looking at the red-black bet, okay? Okay, and notice here with our red-black bets, we're losing $1. We're talking about our net gain again. Okay, we're doing that 20 out of 38 times. We're winning $1 18 out of 38 times. So to get, let's say if they land on red, they lose if it lands on black or green, and win if it lands on red. So they're losing if it lands on black or green, so it's 20 out of 38, and they win if it lands on red, that's 18 out of 38. So we're losing our $1 or we're gaining $1. It doesn't include the $1 that we've actually spent to play the game. So the expected value is just losing $1 20 out of 38 times plus winning $1 times 18 out of 38 times is 5 cents. So after many, 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 many $1 bets, the player can expect to lose about 5 cents. All right, so go ahead and try this one. Use your calculator and calculate and interpret the expected value of X in our NHL goals example. So remember, this one was X is the number of goals that were scored in any random game. So when we find the expected value, that's like saying, okay, what is the average number of goals we can expect in any given game? So go ahead and use your calculator and try that. Hit pause and then take a look at the answer. Okay, so the expected value is basically, remember, you're multiplying each value times its probability, okay, adding all those together to get your expected number of goals that you can get. So what does the interpretation mean? And remember, it's always in the long run. It's not after one game. So in the long run, you can expect an NHL team to score 2.851 goals in a game. Obviously, it doesn't make sense. You can't score 3/4 of a goal, but due to the probabilities, if you round that up to 3 or down to 2, it's essentially changing those probabilities. So do not round it, please leave it. So in the long run, please make sure when you're interpreting it, you put it in the long run, in context, and do not round the expected value. Okay, so go ahead and try this one on your own. This one we're taking a look at a baby's APGAR score, which we've taken a look at on previous questions. Notice how X is defined. X is the APGAR score of a randomly selected newborn. So when it says value, you know what that means. That's the score for the newborn, and this is the probability that each of those scores occurs. So compute the mean, that's the same as the expected value, and then interpret it in context. Okay, so notice the notation again. That's the summation of each of the values times the probabilities. Okay, adding those up together, you get 8.128. And what does this mean? It means the mean APGAR score of a randomly selected newborn is 8.128. This is the average. Make sure you include the fact that it's the average score of many, many, many randomly chosen babies. Okay, in the next section, we'll just take a look at the variance of random variables. So go ahead on to the next video to take a look at what the variance will look like for discrete random variables.